Good afternoon. I invite you to the third lecture from the computer architecture course. And our today topic is, in the fact, one of the main topics because we look how the CPU works and process the instruction. There is one motivation picture. It is, you probably know about Google Summer of Code project. So it is possibility to work on the funding of the Google over the summer holidays on some open source projects. So Google provides funding. Now it is a period when the different organizations apply for the funding. And from March 4 to March 19, you can apply for such project. And you can find a wide range from LibreOffice, some web-based technologies, and so on. I have worked as a mentor for students in this project for Nutix operating system and for RTMS, which is a system which is used by European Space Agency and NASA for the space application and so on. And, okay, one motivation picture. Because I work with our students or foreign students, I have been invited to one of the Google Mentor Summit, and it is held in Technology Center in San Jose. And because you want to bring there some presents, and it is quite hard to bring the alcoholic drinks and other stuff to the US, then it is agreed that everybody brings the chocolate which represents his country. So we are here at the chocolate table, and the guy on my left side is Joel Sherrill, which is a founder of OR Corporation and RTMS operating system. And for sure, when you are in California, you probably want to visit Yosemite and some other areas. So this is a picture from my trip to Yosemite as well. Okay, so how to teach and show how the CPU works. You can try to do something directly with some microcontroller, or you can try to attempt something directly on your CPU on the laptop and so on, but it is quite complex. And it is much easier to basically use something smaller, something which represents maybe older time, maybe future time, but for the simple CPU. On MIT, each student for the electronic branch of the studies and computer science builds his or her own CPU during the second year or first year of the studies. We have little lower demands over our students. You only learn how the CPU works here, and if you want to get knowledge how to build your oven and how actual today processor works, then you can attend the advanced computer architecture course. And for the teaching here, we do not build the CPU from the scratch, but we use a simulator. So basically, it is a simulator initially it was a simulator of MIPS architecture, which was one of the architectures designed by Professor Hennessy. It was quite useful architecture because at one time it was used for design of 3D graphics. If you use today OpenGL and such stuff, it was developed on MIPS at SGA company. But then there was more powerful CPUs, and Intel gets its time and so on. So later, MIPS architecture has been shifted to the embedded architecture. So there are many wireless routers and other stuff which is running MIPS. But today, even in this area, it shrinks the use of the MIPS, and ARM architecture 32 and 64-bit prevails. But on the other hand, problem is that those commercial architectures do not allow to build free clones, and you need to solve the licenses and patents and so on. And for this reason, the students at Berkeley, which has been led by the Professor Peterson, so basically the professor who started the first RISC processor in 80s, has decided they build their own architecture, and it was called RISC-V. And we start to teach with this. In the past, in previous runs, we have used a MIPS simulator. It is diploma thesis. It started as diploma thesis of one of my students, actually one of the teachers of this subject. And last year, we decided to do the switch to RISC-V architecture. So, please forgive us if there are some mistakes and bugs in the documentation and in the simulator, because really you are the first year when we started to work with this simulator. You can find another RISC-V architecture simulators. One which is written in Java and is very nice is the RARS, which is again the switch of original Mars, which was a MIPS architecture simulator. It has a very nice IDE, but it doesn't show the internal propagation of the instructions through the processor. There is some X-rays option, but basically it is not what we need. There are some others like RIPES and other simulators for RISC-V architecture. There are many educational architecture simulators for MIPS. This one is interesting that it provides a model where are 3 parallel pipelines, so it is possible to test some more advanced stuff. Okay, there is a download link for our simulator. I suggest to start it now, load it on your computers, or use a simulator on our desktops here, where it is in the development group of the application. If you have Ubuntu, then you can set up the PPA. Again, it is written on the pages, and you can find it on the page of the simulator how to set up it easily. We have builds for Debian, SUSE. We have online version which can be accessed directly on the web. It is web of my students, which is now in Israel, where is at the university. And you can find, okay, some talks about our previous attempt with the MIPS, but this one is exactly in the Czech. But we have been invited for this year Embedded World Conference in Nuremberg to show how we teach computers architecture, so there will be another presentation in English by that time, but it is in the May. Okay, so when we return to the CPU, what are the basic blocks of the CPU? The concept of computation engines is quite old. Some of them has been built as the mechanical systems. Then when we want to have a Turing complete system, we need some memory or some tape to store the symbols. Then we want to have some rules to a movement in this memory and to some conditions and so on. But the modern concept of the processors has been defined by von Neumann, which was Hungarian scientist, and he decided and defined that a processor has only a single memory for instructions and for data, which was a big step forward, which allows to use the CPU to load, for example, your Java application, compile it for your processor, store it into the memory, and then say, okay, this area in the memory is in the fact a set of the instructions which should be executed. So it is big difference when we compare it with the Harvard architecture, which has separate bus for the instruction and for the data. It has the advantage that we do not need so big bandwidth, that basically the instruction do not collide with the access to the data memory, but it has the disadvantage that we cannot load and run a new program without some external tool on the Harvard architecture CPUs. So it is important. Von Neumann allows this. For speed reasons, we usually provide some area of the memory which is only for data, or maybe we use a cache which is separated for data access and instruction access, and we look at it at that next lecture. But generally, today computers allow to rewrite content of the memory where we store even the instructions, and we can use it to basically compile code and run code and so on. So we have there 5 functional units. So memory. Then we have some control path which allows to decode the instruction, and according to the read instructions, it manipulates by data. So it takes the data from the main memory, processes the data in the data path in the arithmetic logic unit, and then stores the data back. In the original concept, there has been defined a special set of the instruction to provide input and output operations. Because if you have only the memory and processor, then basically you do not get any data from the system and you do not put any data. Okay, maybe you can stop it, solder out the memory and hope that the data are not lost and somehow to measure them. But you usually want to have something more convenient, like is this monitor and touchpad and keyboard and so on. And today, those peripherals need a quite wide range of the throughput. So basically, if we have keyboards and it is from time to time, one key, press it, okay, maybe even for some people are able to press 10, 15 keys per second, but it is nothing. It is small throughput. But if you, for example, want to work with the audio, then if you have a stereo at CD quality, then it is 16-bit per each channel, so it is 32-bit, so it is 4 bytes, and we need something like 40 kilohertz, so it is 160 kilobytes per second, multiplied by 4. Okay, I make mistakes quite often in this. So basically, it is not ideal that for each sample at that 41 or 44 kilohertz, we need to somehow instruct CPU to read a sample and send it to the output. So usually, today, that original von Neumann concept is changed a little, that CPU only set up the peripheral to read the data from the main memory, and the actual output of the data is run through the DMA engine. Again, we look at it later. But you should know that basically there is a mechanism that the data are directly stored. For example, if you have a 10 gigabit network, then your CPU has no capability to take all the data through the processor byte by byte when they are arriving. So basically it is necessary to have there a mechanism that the network card stores the data into the main memory, and when there is one or more packets ready, then it informs the CPU that it should process the data. So it is von Neumann architecture. Basically today all usual processors are working with this architecture. For signal processing, there are special CPUs which has Harvard architecture, but usually we have this one. Okay, so we have there those 5 units. Control unit, which controls what should be done with the data, and arithmetic logic unit. And it is so-called processor. And the processor needs some area where to store a temporal variables. We'll look at it later. Then we have the memory, which is relatively slow, but allows to keep a large amount of data and input and output. And then we need that area where we keep the actual values which we are processing. So basically, you can look onto the computer as or processor as on the cooker which gets a recipe. So basically, you have a printed recipe, and you say, okay, then on the first line, start to process and do something with the ingredients to cook some meal, for example. And this pointer, which points to the actual line from the recipe, which informs what should be done, is called a program counter. And at the start, we take the value, we set up to predefined value this program counter. So, for example, it can be on the top of the first page of the recipe. Then we have usually some temporary register. Register is, you have it in the Apollos, maybe some information about this. Basically, you have, do you know D flip-flop? Or if you do not know it, then you can look at the register as single variable in the memory, because memory is again implemented by some flip-flops or some bistable memory cells which keeps the value. So basically, for our actual description, a register is some area when we can store some number of bits at a given time instant. Basically, we can instruct it now, hold the value. So we read the line from the recipe, and then we need some area where we can do a cooking, actual steering of the ingredients and so on. Because you usually do not go to the store or to some another area and there do something. Basically, you take the ingredient, move it to your general purpose registers. So those are the special registers which are in some array. So basically, you can look at it as a very fast block of the memory, which has some specialities, but anyway, and it is directly inside the processor. And there we can add, subtract, and so on the values which are in these registers. We usually want to have there a stack pointer. You probably should know what it is, a stack data structure from the from some algorithms or such studies. Basically, the stack is last in, first out data structure. So it is used to store the actual line in the recipe when there on this line is information. Okay, go and prepare some subtasks. For example, boil the milk or add something, or basically when we need to go to some another part of the recipe, proceed that part, and then return to the main task. So basically when we have some subtask. Again, we have a special lecture for subroutine calling and invocation of the functions of operating system. So I will not go in more details now. Then we have a program status word, which is some area where CPU stores information if it is actually executing the standard user code, or if it is some system code, if there is exception, and so on. Then we have some possibility to enable and disable some interrupts, some external events, which can stop the processing of the CPU and so on. And then we can have there a list of another registers which are defined for special purposes. Because in general purpose registers, you can process any data. As we have said, data in the memory are some combination of ones and zeros, and basically it only depends their interpretation which glasses we use and put over those data. But if those glasses corresponds to the actual architecture of the processor, so basically if we work with signed and unsigned 32-bit integer and CPU has 32-bit machine word, then such processing is easy. If you have only 8-bit CPU and want to work with 32-bit data, then you need a a list of instructions which reads the individual bytes and proceeds the operation. So basically, it depends. If you have there a color and you want to do some complex processing, or for example, you have there a compressed video stream, then if the CPU has special instruction to help this processing and look at those data with those special glasses, then it is much better. So usually processors has support for floating point units according to the IEEE 7 and 504 standard, which we have seen during our last lecture. So, because in another case, you can do a software computation of floating point, but it is relatively slow. So, there is a main cycle of the processor. So basically, at start, we set a program counter to some predefined value. For some processors, it is at 0 address. For some processors, for example, for the Intel x86, it is something like FFFF0 for some strange reasons. For another processors, it can be a value which is stored somewhere in the memory and so on. But basically, it is preset to some defined state, which usually with interrupt disabled and in the some system mode. And then start the actual cycle. So we provide a value from the pointer to the instruction program counter to some bus, which allows us to read a value from that given cell in the memory. So basically, PC points to some array. You can look at the program at this moment as the array of 32-bit words. At this moment, for example, for the Intel, it is much more complex. Then we advance this pointer to the next location, where we expect the next instruction. In the case of complex instruction set, we need to compute the length of the instruction. In the RISC architecture, it is only +4, the next address. We store the contents from the memory which we have read to the instruction register, decode this value, and the first thing which we need to find is what is the operation code. So opcode, operation code, basically it is encode number of operation in some list. So we have one number for addition, subtraction, and so on. Then we need to execute actual operation, which usually means to take the data from the registers and then pass those data through the arithmetic logic unit and then store somewhere the results. There can be a problem that, for example, if you try to divide by 0, that there is exception and so on, but we skip this for today's lecture. And the last step is a repeat again. Okay, there can be some mechanism to lower power consumption, to suspend the execution and invoke it again after some event and so on. But the basic cycle of the most CPUs is this simple. And what are the actual instructions? In the memory, there is only the list, the array of some binary values which encode the instructions. Those are the addresses. This is the machine code. So this is a machine code. And it is quite hard to read it directly. And it is even more difficult to program it directly. Okay, there are people, I have colleagues who programmed the processor up to the operating system with access to floppy drive only in the binary code, but it is hard. So we usually use a C program. In this case, there is a simple example of the code equivalent to the instruction find first bit set. So basically, if we have there a some word, in this case, this x, which is equal to 157, and there is one bit set somewhere, and some others are 0 or non-zero, and before this one there are zeros, then it finds the position of the most significant one in the word. So basically, it is, for example, useful for your conversion of integer value to floating point and so on, to shift it to the left and right and so on. So basically, we need to find this. And how we can achieve this? So we have the output value, which is in this case at start 0. And we check if the x is 0. If it is not, then we divide x by 2. So basically, we cut the least significant bit. And if it is not a signed value, if it is unsigned value, or if it is not negative value, then after some number of cycles, when we cut one bit after another, we need to get a 0 value. And at that moment, we set the value y to the bit number. And there is, in the fact, there is a mistake in this code, because there should be a -1 for the start, because we want to get the value, what should be a result value for 157, if it is a bit position of the most significant bit. Try to compute it. Okay. 7. 2 power 7 is 128, and it is actually the biggest lower or equal value. So in the fact, what it is floor of this value in the power of 2 series. Okay, so this is the C source. Now we have there the assembler, which is this code, which is already rewritten to the actual instruction of the processor. So basically, for example, we say there add to the sum register, which we have decided it will be A0, the value 0 and 157. So it sets the A0 to this value. Set T1 to this value. Then check if the value of A0 is 0. If it is, then branch somewhere. If not, use a divide by 2 by the logical shift right, and add 1 to a T1, and so on, and continue. So basically, you can see that it is easy. And we can look there at this instruction, which increments the y by 1. So it is exactly this one instruction. And when we translate this code for this assembly language, it is called a language of symbolic addresses sometimes, or relocable. Oh, okay. In Czech, it is called jazyk symbolických adres sometimes. But okay, usually we say the assembler to it. And this code is then translated to the actual binary encoding of the instruction. So we can find that this instruction is encoded as this combination of bits, or in hexadecimal, it is not important. And it is stored, in this case, on this address. And because we have a problem to read the values and convert it to the actual instruction, then it is usually useful to have some debugger or some tools which shows the instruction in the memory as already as that code, that you know what it is, operation and so on. You can see it another change here. There we use names for the registers like A0, which means argument 0, and so on. On the other hand, there are only the numbers for the registers, because actual processor doesn't know the names for the registers. It only works with some numbers. Now, how to encode that opcode and the operands in the instruction? At the start, we can think about the 8-bit CPUs from 80s or 70s. And if you want to fit the instruction in the 8 bits, then you can encode 256 combinations there. But if you want to have there some those registers which allows the fast access to some data and processing of the data internally in the processor, then, for example, if we decide that we have 8 registers, then to encode which register is the input and output operand of some operation. So we can consider 2 operand instructions where we have one register which is used as a source, another register which is added or subtracted from it, and the result is stored to the first register. Then in this case, we need 3 bits for one register, 3 bits for another register, so we have only 2 bits to encode the operation. And it is a problem, because in such case, if we want to have there, for example, operation which allows to store value to the memory, then operation to read the value from the memory, then we want some branches and so on, so it doesn't fit into the 8 bits. So for 8-bit CPU, you have one option that one register is explicitly the accumulator and so on, and so on. So it is quite big problem, and you need to think how to optimally encode the operations. For a 16-bit, Intel was 8-bit, 8080, then actual processor started as 16-bit, 8086. So it can basically encode 65,000 combinations. And if you decide that, for example, you have you can have 2 or 3 operands. If you have 3 operands and 4 bits, 4 registers, then basically you have 3 times 4 bits to select the register, and you have only the 4 bits left for the operation. So again, for 16-bit encoding of the instruction, you usually cannot have a reasonable amount of the registers, for example, a 16, and you have problems that you need to use some another encoding. In the fact, complex instruction set processors use some follow-up words and somehow extend the instruction, but it complicates the decoder and so on. So, quite common practice is today to have 32-bit encoding of the instructions, to have 32 registers, which is reasonable amount for a typical number of local variables in some loops and in your code, and 3 operands. So basically we can say that C is equal to A plus B, so we can use 3 registers. So in this case we have 15 bits which are reserved in this case to store the 3 operands, and then 17 bits which gives a reasonable amount of the operations. Problem is that we do not want to encode only the operations between registers, but we usually want to encode even some immediate values, because if you want to put the value 1 into the register, you probably do not want to store it somewhere into the memory as the constant and read it from the memory. So for some range of the constant, you usually want to be able to encode them directly into the instruction. Another problem is that if we access to the memory, store or read the data, then you usually have some structures. For example, if you have a structure for point, then it probably has X and Y components. So basically, if you have a pointer to X of given point, you usually want to have some simple way to access the Y without the need to manipulate with the registers and so on. So this can be solved such a way that we add additional words, that if there is immediate operand, then we know that the next word is not the following instruction, but it is the immediate operand. But such solution has problems for predecoding, parallel execution, Okay, Intel uses this solution, but for example, ARM, RISC-V, and other architectures try to strive with the fixed encoding of the instructions. Another thing is that, for example, Intel has even on its 64-bit CPU some instruction encode directly by the 8 bits. But such instruction, which is only 1 byte long, in the fact, blocks a large area of the 16-bit or 32-bit encoded instructions. Because if you, for example, select 1/4 at 8 bit for some type of the instruction, for example, for the increment of the register, then basically at 16-bit, 1/4 is 16,000 of combinations. And at 32-bit, it is 1 milliard. So basically, it is questionable which instruction should have shorter codes and block the area for a longer instruction and so on. But sometimes it worth to have some such solutions. For example, on RISC-V, they decide that they would use only a 1/4 from 16-bit area and left the 3/4 to store shorter aliases, 16-bit aliases. So this allows to increase the density of the code. So it is the idea from RISC-V. RISC-V defines that if the two least significant bits of the instruction are a 1, then it is instruction which is at least 32-bit encode and reserves the combination 000110 for the instruction which are encoded as so-called compressed aliases to those most used instruction in the code. And because they know that maybe there will be need to add another extension, and for example, Intel has big problem because it blocks short codes by some instruction which are seldomly used, and then a quite often used instruction has too long codes. So for this reason, they decide that they define rule that even 32-bit instruction cannot have those 3 bits set to 1, and it is a space reserved for 48-bit instruction, 64-bit, and so on. It is not used now, but it is reserved for the future that it can be necessary to use it, or can be useful to use it. Okay, so, yes? Okay, in the follow-up cells. And it is question what is the organization of the memory. Today, most of today's processors allows to access the memory on byte basis. Byte is quite useful for accessing and processing text information and so on. So they have a byte access to the memory. But actual organization of the memory is usually today for 32 or 64-bit in the width. So yes, there is a problem if 1/2 of the instruction falls at end of one 64-bit word or 128 word, and the another one goes to another address. But it is hidden by the hardware that it usually some processors and with exception if you try to access the data which are not naturally aligned. So it means that, for example, 32-bit data has to be for byte addressable CPU start at the address divisible by 4. But most today processors are able to cope with it, and even for the instructions. So they can access the data which are not aligned, but it has a penalty. So compiler ensures the alignment. If you do not add the keyword packet to map the data directly to some data which came from the network and so on. But the natural data structures are standardly aligned. Okay, so we know that we somehow encode the instruction. We look deeper how we do it. Now we need some set of those pots in our kitchen, basically that places when we store the data which we want to process, and we have said that it is called the register. And we have there, in the RISC-V processor, we have there 32 registers, but basic general purpose registers. Register 0 is, with the index 0, is hardwired to the 0. So it simplifies some stuff. For example, if you want to address with immediate address, then you can say, okay, add a 0 to it. Or if you want to provide a constant to the register, then you can say, okay, I want to add a 0 with some value, and so on. So this is the reason that we have one register which is hardwired to the 0. Then we have, in this case, it is register number 1, but it can be some another in some another architectures. The return address register, which is used to return from some subroutine if we have main task and ask to run a subtask and so on, and return. We get to that in something like lecture number 7 and so on. Stack pointer, again, to store some data to return in a deeper stack, in the deeper inner calls chain. Then, because we can address only by some small immediate value as an offset to the register, then for this reason there is a general global pointer. It is pointer to some area which is used for global variables. Then we have there a thread pointer if we have a multiple cores and so on. And this is the index. It is index 4. And the name which can be used in the assembly is thread pointer. Same, for example, for those registers which are called temporaries. So basically, those are the registers where you can store the value, and it is not preserved if you call some subroutine. Then there are registers which are preserved if you call the subroutines. So it is callee safe, and those are caller safe, and so on. And then there is some subset of the registers which are used to directly pass the arguments. Again, we can pass arguments over through the memory on fixed location relatively to the stack and so on. We look at it later. It is not important for our start at this moment. And then there is that program counter. For some processors, it is part of the general purpose registers file, for example, for 32-bit ARM, but it is not, it is quite complex for the fast processing of the instruction if you have there some condition branches and so on. So at the end, it is better to have it as a totally separate register, which is not directly accessible and writable by arithmetic logic instruction. And then we can have there a set of another registers, for example, for the floating point operations, and we need some registers for the status and so on. So again, it depends. You can have a processor which has floating point support, which has multimedia support, scalable vector extension support, and so on. But now we focus on that simple processor with integer-only registers. And to process the instructions, then basically we need, okay, there is a general purpose register, but PC is register as well, specific purpose register. And we have there this register, and at each clock cycle, if the instructions are processed in some period, then at each clock cycle, we advance that register by 4. And that way we move to the next location in the memory, and it is in the instruction memory, so we read the actual instruction. Okay, we want to have some branches and so on, then it starts to be a little more complex. But for the start, when we have only the sequence of the operations, then basically we can have this register, and at each clock cycle we advance it by 4, read instruction and execute the instruction. Now we need to look at some instructions. So goal of this lecture is to understand how we can build a very simple single cycle processor which can execute a basic subset of the instruction which allows to build relatively complex algorithm. So we want to read and write data from the memory and to the memory. So there is load word instruction which loads a machine word which is 32-bit in our concept, store word to store the data word into the memory. Then we need some operations which allow to combine two values in the registers and store result in the third register. Sometimes it works to have the operation which adds the immediate value. For example, we want to advance some pointer by 4 bytes to the next word in the memory and so on. So those are the variant of the instruction which end in this case by I, which means that it is immediate. Sometimes we want to load even more than some relatively small number of bits. In those instructions with immediate operand, we can encode only 12 bits, which are signed extended to 32, but it is quite small amount. So we want to have some option how to read and store longer constant in the register. Then we need some operation to compare two registers and allow a branching. So basically we can build some conditional code. At the start, we start only with the branch on equal. So if we want to compare which register is bigger than another, then we need to use this operation the first, which is set on less than. So basically, if one value is of the first register is smaller than in the second, then the output is set to the 1. In another case, it is set to the 0. And then we usually need some operations to call the subroutines. In this case, in the case of RISC-V, there is in the fact only, there are only in the fact two operations, jump and link over the register, and they can be combined such way that we can get even the return instruction from it and so on. So again, but it is for the another lecture. And the CPU consists of the control unit and arithmetic logic unit, which is our data path, and registers and so on. And we implemented as a single cycle processor. This has some disadvantage that we need to wait till all the logic circuit settles before we can start the next instruction. So it will be very slow. This is the actual definition of our instruction. So basically, we see there how we write it in the assembler. So it means load word, destination register, and immediate data plus one of the source registers. So, and there is the meaning. So it takes looks into the memory at the address which is given by the value read from the RS1 from the register file. We add the immediate 12-bit data, signed extended to 32-bit, and store the result to destination register. Then we have the operation again, store the value in second source register to the memory, add immediate data to register and store it in the destination, add to register together, subtract them, and so on, do some operation between the registers, and then there is a compare one, another, and if they are equal, then we go to the next instruction. If they are equal, then we go to the address which is given by program counter and some offset. So basically, we can build loops of some size. And if the condition is not true, then in such case, we go to the next instruction. And then there are those special instructions to call subroutines. We skip them for now. And then there are two instructions which allows to set a register to a full 32-bit value. Basically, we cannot encode 32 bits into 32-bit instruction because then there would be no space for operating code. But if we provide a combination that one instruction set, for example, in this case, upper 20 bits of the instruction of the destination register, then we can add a 12-bit, which is allowed by this instruction, and form by two instructions. So in the 8 bytes, we can load a 32-bit value into any register. And for all the operation, everything is signed in this case. Okay, we return back here to the MIPS, which we have used for the teaching in last year, because there it is quite easy. In MIPS, we have 3 types of encoding of the instructions. In most significant 6 bits, we store the operation code of the operation, and then we have there one source register, second source register, and destination register, and the function for those 3 operand operations. And for the immediate operations, we have there a 16-bit of immediate value, and this register which changes the no, doesn't change. In this case, it is a source register, source register and destination. Yes, it changes the meaning. So this is for 3 operand. It is source, and this is the destination. So basically, we add those 2 values and put it there. For the immediate, we take this value plus this value from the immediate part and store it here. And so the register changed the role from the source to destination. And it is even worse because for the operation which stores data into the memory, we have this as the source and this as the source, and it stores the data to the memory. So basically, it is the meaning of the registers is changed, and for fast execution, when we need to compare data dependencies between registers, it is a big problem. So for this reason, a RISC-V encoding is a little different. So they decide as the priority that position of source register 1, source register 2, and a destination register doesn't change in any case. But what it means? This means, and operation code is 7 least significant bits, but the last 2 are 1 for 32-bit encode instructions. And we have operations which really want to work with all 3 registers. So it has some opcode, one source, second source, they add them together, for example, and put the result to the destination register. And the actual function, because we have there some unused fields, then actual function, that it is addition, subtraction, and so on, can fit into those values. At the moment when we want to add the immediate value, then they decide to keep only a 12 bits, because the code space is quite small, and to put the data inside is a problem. So they decide that they have only 12 bits of immediate operand. They keep the position of the source operand. Function says if it is addition, subtraction, and so on. And we store the result into the destination register. Still clean and relatively well readable. But things starts to be worse for the operation which stores the data to the memory, store word. Because in this case, we have 2 source registers, no destination register, because destination is the memory. And we want still to have an offset there to offset that another fields in the structures. And we want to keep it at the 12-bit. But this part of this immediate area from the previous instruction is taken by RS2. So they decide that because we do not need to destination register here, that they basically swap those 2 areas, and the rest of the immediate operand is stored in this area. Okay, it is for reading, it is a little worse, but the actual hardware is better. So the thing starts to be even more complex for the branches, because branches needs conditional branch needs two registers to decide if they are equal or not, and then it needs to branch in some range. But because we define that the encoding minimum length of the instruction is 16-bit, then we do not need to target to the odd addresses. So instead of the branch range of the plus minus 2048.7 bytes, they decide that the range is in the fact multiplied by 2 to the 4096 in one direction, and another direction it is little less bytes. And because they do not want to change the meaning of some other bits, they decide to swap them this way. So basically this least significant bit, which is not used, is in the fact remapped to bit 11. And bit 12 is kept as the most significant bit, because this bit is needed to extend the sign, and for the reasons that there is a limited logic gain or fan out of the gates, they decide that this bit will be optimized and kept for all instruction as the most significant bit, that bit which is sign extend over the some another area. Then there are another instruction which has a 20-bit immediate operand. Those are those which can fill the top part of the register. And last one are jumps. Okay, we skip them probably for today, which allows to branch in the 2 times bigger range than is provided by the unsigned. Okay, but so then 20. Basically, it is half of the millionth instruction forward or backward from the actual position. Okay, 16-bit instructions, which is enough for most of the code. Because yes, if you want to branch further, then you can prepare the full 32-bit value in the register and branch to that value in the register. But for this, you need more instructions. So, and you usually keep with one block or library in something like megabytes. So, okay, it is reasonable. Okay. So opcode specifies some group, then actual function, if not all other bits are used for immediate, defines a function, and we have one source, one destination, and so on. And we have 32-bit general purpose register, and register 0 is hardwired to the 0. There is another picture. If you want to build an immediate operand, that basically the 12-bit operand is encoded by those 12 bits, and the last bit is signed extend to 32-bit. Again, for this case, but we use different bits from the instruction. So basically, this is a table which describes how to build a decoder which decodes the immediate value from the instruction. And what is the goal is to have as much as possible the bits at the same position. So basically you see that, for example, for those who do not need any multiplexer, that if those bits from 5 to 10 are in use in the instruction, then they come from the same location. For this, For this, you need to switch between 2 locations. For this, between 2 locations, and for this, you have 2 locations plus a sign extension, single location, sign extension, and so on. 2 locations and sign extension. No, 1 location and sign extension, sign extension. So it is quite clever, but little complex to understand. You do not need this for the actual work with the processor, because you write an assembly language program which is then translated to the machine code. And for our set of the instructions, we use these operating codes which are defined here. As you can see, for the group of 3 operand instructions, we use only a single 7-bit opcode, and the actual instruction is then encoded in the rest of the, or operation in the rest of the bits. For this operation, it is directly a single operation for a whole 7-bit opcode. And for those, it is somewhere in between that we use those 3 bits for the encoder operation, but not those 7. Those are because those are used for the immediate operand. It is quite clever mechanism, and in the fact, this optimization of the encoding and implementation of the processors was a reason the book Computer Architecture Quantitative Approach from the Hennessy and Peterson was used, yes?
Could you go one slide back, please?
Yes.
Why is subtraction, why is it encoded in the opcode and not in the...
Because we do not want to block too many opcodes. It is attempt somehow to compress the instructions, because we have seen that for immediate for the 3 operand instruction, we do not need all those bits which are used for immediate and so on. So we can reuse them to encode actually if it is plus, minus, and so on. And from the circuitry of the CPU, it is easy because this encodes that it is some arithmetic logic instruction. It sets up the data path, and those function only controls what will happen in the arithmetic logic unit. We will see it later. Okay. Now we try to build our CPU. So it is our goal. We try to build it. And the first thing is that we want to have some single 32-bit register. For your case, if you do not know flip-flop circuits and so on, you can look at the register, in this case, as a sum box where we store a value which is coming from the left at the time of clock signal. So basically, each time when we start the instruction, we store what was there on the bits, that PC apostrophe, and then from this time we hold this value on the output. For the instruction memory is only the combinatorial circuit. Basically, we set the address, 32-bit address, which defines which word. Okay, in the fact, it is only 30-bit because last 2 are not important for us because we take 4 bytes at each read. So in the fact, we use only the 30 bits on the input, and it selects which positions in the memory is used. For sure, we probably do not have a single memory over 4 gigabytes of address space and so on. But for the start, we can look at it this easy way. We can limit it, for example, to some small range and so on. For a data memory, it is more complex, because for the data memory, when we want to read it, then we provide the address, and on the output, we have a data. It is easy. But at the moment when we want to write a data to the memory, then we do not need a read port. And at the time, we want to feed a data there to the write data port and say this clock cycle has computed the value which should be stored to the memory. So we set up a write enable signal, and at the end of a given period, which is given by the clock cycles, we store the actual value, new value, to given location in the memory. Then we have there a registers block, which is quite complex, but it is small. In our case, we have there a 32-bit register. So basically, we have there 32 such locations. as is this single register here for the program counter. And each of those registers can be addressed by 5 bits to be read. So we have there a 32-bit values, and we have there a multiplexer which selects according to this 5-bit value from which of those 32 registers we want to read data to a read port. And because we want to process the operation between 2 registers, then it is advantage to have 2 read ports that at single clock cycle we can in parallel read one source register and another source register. So we have there, it is usually shown as a multiplexer, so it is usually written this, and we have there a 1 and in parallel another 1 which selects the another output, so it is RD2, and this one provides RD1. Okay, so it is for the reading. It is combinatorial circuit. We provide 2 5-bit values here, and we get a data. But we want to store a value even to the register, and it is done such way that we take the write data value, bring it to all the registers, but enable the write here conditionally by 5-bit address only for the single register. So we take the 32-bit data, provide it on the input of all the registers, but only that one which only in the case that we enable the write and a register is addressed by some decoder. So basically there is some address decoder which has 1 line for each register and enables that the data should be written at the next clock edge. So it is the register file. Do you see this data structure or what it does? Basically it is array of 32-bit values for you in the memory, when we can at given instant of time write at one index a value which is on the write data, but not each time, only when we want to write it. And in parallel we can read 2 values in this case. Okay, sometimes we have registers files which allows to access even more data in parallel and so on, but for our actual case this is a block which is enough. And then we have this, in the fact, most complex block, which is arithmetic logic unit. There are that others, multiplications and so on, shift and so on. But for our design, we can look at it as the black box, which we only control what operation should be processed, if it should be plus or divide or multiplication between 2 inputs. And on the output we have 32-bit result and some indication if the result is 0 or not, for example, or something more. In the fact, internally we can build it, if we do not look at the power consumption, as more blocks to which we bring, for example, this can be the other, there can be a multiplication, so we put there the values, and we compute those in parallel, and on the output we select which one we want to use according to this selection of the operation. In real processors it is done usually more clever that we do not drive the power into the multiplication when we need only addition and so on. But for the start we can start with this simple way. And now we have our load word instruction. So what it is a load word? It is the instruction which should store the value to the destination register from the memory at the address given by one source register and, in our case, immediate offset, signed extended. We can encode it because we have already decided what would be a code here. So this is the opcode. In this case, operation number 3. Function specifies if it is byte, long word, and so on. So we do not need to take care about it. And then this is how we write the assembly language, and this is bit by bit encoding of the instruction. So there are those bits which represent the immediate value, source operand, which is this one which defines the base address, then destination register, and so on. And the example is load word from the address 400 to the register X2. And if we encode this by nibbles, then we get this value in the memory. And there is we can see that if we want to encode the 400 as the immediate value, that it is really here. And then there is 0, which is a source register, because we want absolute value. So we want to add a 0, which is in the 0 register. And destination register has the value 2 here in those bits. And we can implement our hardware. So it is the encoding again. So it is the bits which we have. We have there a program counter. Program counter provides the address of the instruction. We read the instruction, which in our case we will expect that it is the instruction to load word. We provide a bits 15 to 19 from the instruction. We provide to the input first input of the register file. Register file provides the actual base address for the addressing. Then we select that we want to write to the register given by those bits. And some part of the instruction, those bits, that immediate part, is decoded to 32-bit signed extended value. And we put the result to the arithmetic logic unit. We get the result, which is the address of the memory location. And the memory responds with the data at the given cell. And we need now to provide the data back. So basically, we read the data, and those data are passed to the write data input of the register file. And we need to select that the data should be written at the end of this clock cycle. Data are written, and our instruction has been executed. Simple. There is one thing missing still. We need to advance our program counter to a next instruction. So we add there the increment by 4 to next instruction. And now if we have sequence of the read word instruction, or load word instruction, then we can execute one after another. Okay, I try to demonstrate the result. We have started our simulator. We select that we want a simplest possible CPU without pipeline, without cache, and so on. And we select that we want to start it empty, without a program. And okay, you should see something like this. There is a model of our CPU. And now we can load the example. And there is directly in the menu example, simple load word, store word with internal assembly code. And if you look into this code, then there is nothing more than a single instruction which loads data from the address 400 hexadecimal with a base register 0. So we can try to compile it. This is done by this top level blue arrow down. So it compiles, assembles. And now what we see, for some reason the start address selected here for our implementation is 200. Then at this address we see the instruction load word, and it is followed by store word. It is our next task. And if I extend this window, then we can see that it is encoded exactly as we have seen in the presentation. So it is the encoding. Now it fits there. If I make it small, it doesn't fit there. So I do it this way. And if we look at the same address here, at the address, because on the right, we have the memory window. So this is the memory window. And this is another memory window which looks into the instruction memory. But in this case, in the fact, our architecture is Harvard, is for Neumann. So if I go there, then I can see that I see there on the address 200 our actual instruction. And we have this defined that a data start at the address 400, and the actual data are 1, 2, 3, 4, 5, etc. So if we go to the data, I can say that I want to return to the 400. Then in the memory window, we now see the value. We can look what happens in our core. There will be a problem that it is not well seen because it is too small, but you can zoom it. So I try to zoom it a little. We do not know, okay, actual instruction, next instruction is not defined, but we do a step here. And at the time of the step, what we see, the actual value from the instruction memory, that 4, 0, 0, and so on, is provided here. Please for you do it on your computers because it is better seen than on my here, okay, on the projector. Then, if I go there, then we select register 0 and register 0. Value from the register 0 is 0. And the value from arithmetic logic unit is 400. And 400 is the address to the memory. So basically it goes to the right window here. And a memory has sent a command read data, memory read 1. So it provides the data here, and a data goes down and return back to the write data port of the register file. And the actual register to which we want write, it is maybe more complex here, it is this wire. It says that into the register 2 we want to write a data. And we can see that we have made exactly one cycle, and that the value is in the red, that the value in the register x2 has been changed to this value. So basically you can trace what happens. Now we want to store the red data to some another location. So we want to store it to the next location, which is 4004, and again against the register x0. So we execute the operation, and we see that in this case the register number 2 has been selected as a source to write a data to the memory. 0 has been selected for the second input. We compute the 0 together with the immediate value which is extracted from the instruction 400. Have there a 404, and 404 is the result address here, and in this case we select there that we want to write to the memory. So not read, but write, and in this case we store data to the memory, and we can see that value there actually change. And then there is a branch which can select, if we select the branch, that branch selects, there will be a branch, and because there is a 0 output from the, because register 0 and register 0s both form 0. Then we have a 0, and the program counter is preset to the value, to the next value in the next cycle that we return back to 2, 0, 0. So this way we can build a full cycle, which I can step by step run, or I can run it, for example, 10 instructions per second, and when I write there some value, it copies the value from one memory location to another. Not too much, but if we add there some LED diodes and so on, we can have a full system which start to control something. Okay, I return to the presentation now. So now we advance to the load word, to the store word. So we have seen load word, how it works, and now the store word. Okay, this is the presentation how to test it in the simulator. So in the simulator, you can see that there is a button which select in which mode the processor should be run and allows to load the even the external compiled application. The another button which allows to restart the application, and another one which allows to run, stop the running code, single step, build the code in the internal assembler. If you open the editor with for the new code or open the external code, you can store the code in assembly language. And there is a possibility even to call the external make utility when you can compile actual C code. Then there is a view of the code memory and data memory, and because at the end our actual design is Harvard architecture, but at the end we want to have a von Neumann which has a possibility to change the code through the data memory. Then in the fact those views are into the same memory, but in this one, in the view, we have a decode instruction. Then we have there the core view. We can have there some caches, peripheral, terminal, and so on. We can have there even a simple graphic display. Okay, so it was a load word. Now we want to implement a store word. We see that there is a problem that because there is a second source register, I write it as a T, ST, because I want to have a single character for this representation of the bits is there. Then there is a first source register. We do not need a destination register because destination is memory location. So we reuse those 5 bits for the immediate data. And we have there the immediate data at the start of the instruction. An instruction takes a second source register and stores at the first source register plus a 12-bit immediate value. So there is the encoding. As you can see, we cannot encode all 4 0 0 to the first part of the immediate operand. It is necessary to encode it into those 2 parts. Then we have there, okay, and we have there a combination of source register 2 to store data and the 5 as the base. So it is a little different that in the example you have a base register as a 0 as well, but in this case we want to use a base register number 5, so it is seen there in the encoding. And opcode is 35 in this case. And the actual data in the memory which you find is this one. And the implementation. So what we need to do, we need a second source operand, which is that actual value which will be stored to the memory. So we need to bring those bits from source operand 2 here. The rest is the same. Immediate operand, that immediate part needs to be combined a different way. It is combined from the bits 25 to 31 and 7 to 11. So there is a change that we have a little different decoder and this part is not used. We put the immediate value here, we put the data read from the register number 1 here, and we have the address. And in this case, we do not read data and store them into the register file. So we select that we do not write a result to the register file, but we set a control signal that we want to write to the memory. And execute the step. And for addition, when we want to add 2 registers together, then we encode. We know already that there is place for source operand, destination register, second source register, as you can see exactly on the same place. So if we have operation at register 2, register 3, and put the result to the register 4, then we encode it this way. Destination, first source, second source, then there is an opcode, and there are the bits which are not used for immediate operand, so we use those bits to select the actual operation if it is addition, subtraction, and so on. And the implementation. What we need to add? We have there a second read data register, which is not only provide to the write data to the memory, but we need to select that in this case we have no immediate operand. So instead of immediate operand, we select that we want to have 2 operands read from the register file. And another change, we want to write to the register, but it was same for load word. But what we need to do is to bypass the memory. So we bypass the memory. Select that source are 2 registers, bypass the memory stage, and store the data to the register file. And we can modify this to another different operation, subtraction and or XOR and so on. And we only change what will be done with the arithmetic logic unit, that it will not be the addition, but that it will be some another operation. Okay. And now we want to add the immediate operand to some register. Again, what we need? 1 source register, 1 destination register, but it is same as it was for the load word operation. And we have there a space for 12-bit immediate data. So in this case, we again select that we want to use the immediate data, not the second register. First register, and the output is again bypassed and doesn't go into the memory address. Basically, it is bypassed and stored to the write data of the register file. Okay. And if we want a branch, what it means a branch? We want to compare, if it is branch on equal, we want to compare 2 registers. But we have there 1 source register, second source register. So it is easy. We take 1 source register. We have possibility to select that we want to provide a second source register to the arithmetic logic unit. We ask arithmetic logic unit subtract those 2 values. If the result is 0, and it is a branch instruction, then in such case, we do not advance to the PC +4, this way, but we change there a multiplexer, which selects that at this moment, we advance to previous value of PC plus that immediate value, somehow decode to this shift by 2 and so on. It is not exact in our case of the RISC-V, in the fact that it is done already in the decoder, that shift or multiplication by 2. But anyway, it is somehow provided here. And we add the value of the PC with those immediate value new address from the program counter. So it allows us to branch in some size like 4 kilobytes of the memory. If we have need for a branch footer, then we need to do a vice versa condition and put there some another branch instruction in unconditional, which allows bigger span, or we need to branch over value which is read to the registers and so on. But for 4 kilobytes it is enough. And we have a branch on equal. And at the end we have there a full processor data path which is single cycle, so only program counter, registers and memory are clocked. And we have there a problem. We have there a problem with the speed, because at the moment when we select the instruction, here, store the next program counter, we need to wait for the time to fetch the instruction. In the fact, there is running in parallel the addition, but it is fast, so we do not need to consider this path. Now, we take the instruction, decode it as the value of the address to select a base register for our arithmetic logic operation, and we need to decode the immediate operand. So we need to take a longer from those two paths, because it would be time when the address settle on the address input of the memory. And then a memory has some access time and provides a data, and we store those data there in the register file. So basically, if we start to clock the processor faster, then those logic blocks, big piece of logic, propagates the signal. Then we store incorrect value, some intermediate data, some transition, some hazard in the register. So we cannot clock this processor too fast. There is some realistic computation for relatively old technology. Today it can be faster. That if we have those times and we find the longest loop in our design from one register to another register, because we have the register, then it takes some time after the clock racing edge, when the data are captured, propagate on the output, then they need to propagate through whole the logic, and then there has to be some setup time before the data are correctly accepted by the clock on the next registers or memory and so on. So at the end, we end with something like 1 megahertz processor, which is quite slow. Today, processors divide the instruction execution to small parts, use clever techniques, and so on, and you can get to something like 30 milliards instruction per core in the 1 second. But the processor are able to execute 3 instruction or 6 instruction, 8 instruction in single clock cycle. Clocks cycles can be as fast as 4 gigahertz, and so on. So, okay. Now, how to finish our design? So we have seen that we have somehow encoded the instructions, and that then we have there some data path, and we need to add the control unit to our processor. And control unit can be added as a symbol table in this case. Our CPU doesn't need some sequential processing. If you have a complex instruction set processor that it usually reads the instruction, then need to read another words and do some sub operation. Our processor in the single cycle is able to do everything, and only thing which we need to do is to set up the control signal. So basically, we know that, for example, for the other operation, we need to check that there is this opcode, this function, and this function. And in this case, we say that ALU source is from 2 registers, ALU control is addition, that we do not want to write to memory, that we do not write, that we want to write to the register. No, memory to register, no, 0, 0, 1, that it is not branch, not branch, not branch. So basically, this way we know how to set a value. For store words, for sure, we want to say that it is mem-write operation and it doesn't read the value from the memory. For load word, we say that it is not mem-write, but we want to provide a register memory to the register, and so on. For branch, we set this. So basically, it is simple table, or you can write it as simple expression in VHDL or something like that. And if we add this control unit here, which decodes those 7 least significant bits as the operation, and then conditionally sometimes it decodes a function from those 2 and connect these control signals to our processor, then we are done. So basically you have seen how to build your own processor. And okay, the control unit, which in this case is that simple table, can be much, much more complex. It can be done as a microprogram engine, which takes some data, process the operation to access more location in the memory and so on. And then things start to be much complex. And okay, in the processors, I think that it is better to use this fast parallel RISC architecture. But sometimes you can use those state automatas, which has been initially developed for the microcode processors for something else. So basically, one option is that basically the state is represented by 1, and each time when we can move to the next state, we pass that single one through our chain, and it selects some operations. And again, when this is finished, the wait is finished, so there is no wait, we propagate the one there, and we zero this value, and so on. So basically, you can have the moving one, which moves through some chain of flip-flops and controls the state machine. Or you can describe the state machine by finite state automata. Have you some theory with Mealy and more state automata, finite state machines? Okay, so it is standard technique. It can be done such way that, for example, you have there some combinatorial logic, and then you have there a flip-flop which holds the state, and you combine the state and inputs, get some outputs, and a new state, and so on. So basically, you can advance through such system. We do not go to the depth in this. The combinatorial part can be built, for example, this is a simple logic. Basically, you can express any logic operation from some combinations of the signals as a combination of min terms or max terms. Again, it is from, if you will have a subject, it is logic system and processors, then this LSP, this goes into the depth in this way. But basically, if you have some way that you can combine and say, this signal is set and this signal is not set, then we want to activate this line. And if this line or this line is activated, we have something on the output. So basically, you combine and or gates, you can build such different kind of the controllers. And you can have there microprogram counters. So basically, you can put a smaller CPU inside the CPU, and this smaller CPU with fixed program can interpret the instructions. Okay. Today, a microprogram control unit are okay. On Intel, you need a microprogramming because some instructions are so complex that they need to switch to this microprogram base, which they used in the past. Because initial idea was to have complex instruction which can do some fancy stuff by single instruction code. Today, it is attempt to have instructions which are simple and can be executed fast. Okay, so this is a difference between a reduced instruction set computers, which in the fact returns back to the time when directly a bit encode inside the instruction activates through some simple table the data path and the units inside, and it is not necessary to process and decode the instruction in the multiple cycle. We then switch to pipeline variant, where we start to execute some parts of the instruction one after another, but the actual decoder is very simple, and it is attempt to have it defined exactly only by those single table. On the other hand, complex instruction set computers have the idea that if we encode a complex instructions which can do some more work, even at the price that we need to interpret that instruction more complex way, that in the fact we compress the code and that the narrow bandwidth between the memory and the processor for reading instruction will be preserved. Today we have a caches and so on, so it is not necessary usually. Okay, and this is, we have finished with that same CPU main cycle, which you have seen, which is exactly start from some address, read instruction, go to next instruction. If there is a branch, then maybe you can branch to some another location in the list of the instruction, decode instruction, and execute it by passing data through the data path. And then you can check for some exception and so on, and continue again and again. And we can try to do something a little fancy, which is in the fact start of your seminary. So try to look at the simulator. You can download it for any architecture, almost any computer you have. If you look at this example here, then there are some pragmas, which are special operations in the C language. They are defined that you can have there a preprocessor pragmas. So basically, this is something which is only thing which can be in the C, and it doesn't result in the error if the compiler doesn't understand to it. So we have decided we have those pragmas to select which registers should be shown and memory should be shown and so on. So it is only that when we compile the code that it opens the correct windows. Then we have there some directives. Directives in Genius assembler start with a dot, and we say there that there is some global address of the start of our program. So it is the reason here. Then we can set some options and no order and so on. It is not so important. Then we say, okay, follows the text. And if there is something on the left which ends with the colon, then it means that the symbol will get the address of the location where the next instruction or data will be stored. So this is the start. We can say that the same address is even the loop. There is a load word to register number 2. We can even test what happens if we try to change the value here, because our code allows to edit it here. So we can say, for example, svx2 directly in the memory 1028, but in this case x5. So it is exactly that code which has been shown in the presentation. But I return back to my code here. So with the offset with the base register 0, and we have there store word and then the branch. And branch continues, ask the processor to continue on this location. We can put there even some knob operation, or for example, e-break is execution environment break, which allows to stop the execution. Okay. And we have there an area which is called data, we have set up that it starts at address 400. If we do not set this address, it would follow after the instructions. And I have there some source value, and it is named as a label. So I can use this label here. I can say, okay, src val, and there I can say DST, destination, the val. And this way, no, I have put it. Okay, val. So at the moment when you write it this way, then it is position independent, that you can compile it to any location you want, and it still will work, as you can see here. We can do even something more interesting. For example, we want to add two values. We want to build a calculator. So basically, which adds two values. So we will have a source A. Then I want to have there a source B. And put there some value, source B. Because I want to have it easy to check that it does what I want, then I put there all the ones in hexadecimal. I try to compile, and then there will be complaint because source value is not found. It is the error here. So I need to put there a source A. And then there is a special pragma which sets the address in the memory to which we see at the startup. So if I correct it, I hope yes, it is compiled now. So we have there source, second source, and if we have two sources, then we can try to load this to the register number. For example, 3, the second source. B, register number 3. We can try to add them together. X4, X2, and X3. And we can store the result X4 to the destination value. Compile. Oh, no, I have made a mistake. X4, and if I execute this code, then we will see that I execute, load, the register number 2 is read because the value is read from the memory. Second, register number 3 read the value here from the memory, okay. Now I want to read register 2 and 3 and process them here in the arithmetic logic unit. So I do operation here. You see register number 2, register number 3. They both provide the value. And they are marked as blue because they are read from the register file. And register number 4 is written. So we have the result. And now we want to store it. So register number 4 is read, and we have there a value. And if we run it at the full speed, and for example, try what happens if I add 444, I have the, okay, calculator. You probably do not have much use for such calculator, but for example, what happens if I want to add two vectors? So I can say, okay, I have there, I put there the inner loop. I say what I can say. If I want to add two vectors of 4 values, so our source A would not be a single value, but those will be 4 values, for example. And this will be 4 values as well. I change them a little. No. 3, 3, 3, 3, 3. and 4, 4, 4, 4, 4. I should provide a space. Assembler doesn't protect you. So at this moment, if we write the data after the end of the program, then okay, something happens. It can be an exception. Sometimes it is simply overwriting some other data and so on. So now we have two vectors of 4 components each, and we want to add them. So what can I do? I need some counter to compute because I want to have there something like for E equal 4, if the E is non-zero, then continue and do E plus plus. And the other thing which I want probably to do is to have there some pointer. We probably want to have one pointer which is used for the source A. So I would there PA, which is equal to source A. PA equal to source shift A. PB, which is equal to the source B. And then we want to advance PA and PB. So basically. So how can I write this in the assembly? So I say add what is the option how we can set the register to the constant value. We have seen that we have there a register 0, which is for sure a 0. We can add immediate value to that register, to that 0. So I register X, for example, 5 is equal to the 0 or x0, maybe x0, which is a 0. I can write both. And it would be a 4. Then I have, then I want to set address. So I can use a load address pseudo instruction, which is complex, or I can use, okay, maybe I can use I, x6, x0, source A. Seven, 8. It would be a source B. And the destination. Now I do not want to read a value from the fixed address, but from the actual value of the x6. So over the pointer. So in the fact I have done the A. Do you see it? I really write, in the fact I write a C code. Okay, only in assembly. 6, 7, I access .pb. Now I add the values. I store it. X8. And what I need to do now? So it is, I have done that's is equal to asterisk PA plus asterisk PB. So what can I do there? I need to increment our pointers. How would I increment the pointers to point to the next location in the memory? Try to think about it.
What infrastructure is this?
32-bit. For yes, other E, so immediate to x6, x6 for sure, the 4, and all the same for the other registers. This is PA plus plus if it is pointer to 32-bit location. 7 is 7 and 8. And what is the last thing which I need to do? I need somehow to count our cycles. So it is from our 4th cycle. I want to do no I plus plus, but I have made a mistake here. I minus minus. So what it is? What should I write here as the instruction? E. And I have put the 4 to the register number 5. So it would be a register number 5. Minus 1. And now I need the condition. Okay, it is not full 4 cycles because we do not have check that it should not run. It is do while in the fact. So it is B N E x5 x0 in an error. And maybe it compiles, maybe not. No. The ST not found. The ST, no, it should be the ST val. The ST val. Compile. So we have there one vector, another vector, and then space for the result. So we can try to execute it. Load word. So we have float 1, 1, 1. We have the result here. Oh, no. Okay. So we have the result, and now it is important if it is stored where we want. Yes, so we have the result. And now we should move to the next with the counters. Do you see it? Pointers move to 4, 4, 4, 1, 4, and 4, 1, 24. Yes. And we should subtract the value 1. It is 3. We go there, and we have the next result. And this way we can continue forever. And now we have okay, your first stable processor written in assembly language. Okay. And if we want to run it only once, then we can break this loop here and let it finish and stop on the breakpoint. So at this moment, we run it, it runs once and stop at the breakpoint. No? I have not recompiled probably. Back. Yes. Yes. Break. And our processor has been stopped on the breakpoint. So it is even the practical video for practical part of today's seminar.